So yeah, as I was saying, let's see, here we go. And then finally, the health hazards of volcanism, another thing I'm going to touch on today, and we're interested in there, sort of the acid gases, I think I'm going to show a little bit of how we can sort of quantify health hazards using satellite data. So most of my work and work of our group is using UV satellite remote sensing. So we have a long sort of record, basically, that several NASA and ESA missions have pieced together a long-term record of volcanic degas or UV measurements over since 1978, beginning with the total ozone mapping spectrometer instrument, TOMS, and moving through several other instruments to the present day. And the title of my talk, on the Aura satellite with the OMI instrument, was a major responsible for major advances in this field, beginning in 2004. So that was the sort of the nod in my talk to the Aura mission, which is responsible for many advances. So I'll mention a few of these newer missions in a second. But so just to put satellite measurements in context, there's a lot of other ways of measuring volcanic gases, of course, and ground-based, in situ, and airborne. A lot of developments going on in terms of the use of UAVs to measure volcanic gases. And so on this plot, I just tried to show the different sort of information they convey. You can think about a space composition and a time axis, and some of the more in situ measurements, of course, can give you a lot of compositional information, but on a sort of relatively small spatial scale and short temporal scales. Satellite measurements are generally fairly restricted in composition mostly to SO2, but of course cover large spatial scales. And the advantage of satellite measurements is that you can, they're collected consistently on a daily basis, and you can average them over long periods over time to get a sort of unique idea, if you like, of long-term degassing from volcanoes. And then things like direct sampling of gases give you a lot of compositional information, but are very very localized in time and space. So all these different techniques have their strengths, of course, but just the satellite measurements have some unique sort of advantages in terms of the sort of long-term averaging aspects. So I wanted to just show some recent sort of highlights, if you like, of sort of new sensors we've had to monitor volcanic gases, volcanic emissions. This is a view from the Deep Space Climate Observatory, which is a satellite 1 million miles away from Earth, at the Earth-Sun Lagrange point, where it's got a sort of basically a view of the sunlit side of the Earth as it rotates. And there's an instrument on this satellite called the Earth Polychromatic Imaging Camera, or EPIC, which is a UV and visible instrument, and collects nice sort of visible images of the Earth on an hourly basis. And this is a kind of a unique way of observing the Earth and the UV, and because of the high time resolution you can get hourly time resolution. And this is a view of, you can just see, this is the Raikoke eruption in the Kuril Islands in June last year, which seems a long time ago now, but it's only a year ago. And you can just see the sort of ash cloud popping up through the clouds as the Earth rotates. So this, and we have an SO2 retrieval from this instrument, from EPIC, just shown on the left here. And like I said, the unique sort of thing about this instrument is the hourly time resolution, which is unique for the UV, and gives you, we can get an idea of the sort of mass flux of SO2 during eruptions, during the eruption process, and also the green contours here show ash concentrations, so you can look in more detail at the sort of separation and distribution of SO2 and ash clouds. So we have, if anyone's interested in using these data, these data are publicly available, so I'm happy to talk offline about that. Another sort of recent development has been the increasing spatial resolution of UV measurements by the UV tropomi instrument on the Sentinel 5P satellite. And this is, so these have a pixel size of around 6 by 4 kilometers, very high resolution for the UV, and is allowing us to better identify the sources of SO2 emissions And this example here is from the Kilauea eruption in 2018, and just allows you to distinguish different sources of SO2 much more accurately than we have been able to in the past. Another recent sort of highlight I wanted to point out was this was presented at the EGU meeting last month, I think, by the Belgian group working with the IASI. And this is the discovery that IASI can measure volcanic hydrogen chloride emissions, which is we've had some limited measurements of HCl in the past from profiling instruments, but this is a nadir mapping instrument capable of measuring volcanic HCl, which is quite exciting. HCl, as I mentioned earlier, is important for impacts on ozone, and there's some interesting solubility differences between SO2 and HCl. So looking at relative amounts of SO2 and HCl in volcanic clouds provides some information on volatile sort of degassing during eruptions. And again, this is some pictures from images from the Raikoke eruption, where there was some differences in the HCl and SO2 emissions early on in the eruption, and then later on some HCl was emitted. So again, sort of a really interesting new data set. So this is the kind of the matrix I sort of keep on which to sort of summarize, if you like, all our capabilities for monitoring volcanic gases from space. And so on the left, we have a lot of different, a bunch of different UV and infrared sensors. And on the top, we have the various volatile species we can measure. And, we can see that the observations we have are dominated by SO2, of course, but increasingly, we're getting a little bit of a better picture on the sort of total volatile composition of volcanic eruption clouds from instruments like IASI and some of the UV instruments as well. And but these other gases are mainly only really measured in the explosive eruption clouds, not the passive degassing emissions. So there's still a very strong compositional bias towards SO2 for the passive degassing measurements. We can't really measure a lot of these other species in the lower level degassing emissions. So having a lot of different instruments measuring SO2, of course, is valuable because it gives us some idea of the sort of uncertainty on the mass loading from eruptions. And because they all, generally speaking, these different techniques do give slightly different values looking at the same eruption cloud. This is an example for Raikoke again. This is one of the biggest eruptions of the last decade in the Kuril Islands of Russia in June 2019, and we have a sort of response team that tries to produce SO2 retrievals whenever these events happen fairly quickly, and they typically give somewhat different results. They all use different algorithms, some different assumptions. The satellites have different timing, different spatial coverage, and so forth. And on the left here, we've got IASI data. We've got two different analysts analyzing tropomi data, and we've got some AIRS data, infrared. And they all give slightly different results, but by using the spread gives you some idea of the uncertainty. And this is useful for certainly for modeling the potential climate impacts. So you sort of have some idea of the sort of uncertainty range of these measurements. So we don't fully understand the reasons for the differences we see here, and it's we don't really understand which is providing the optimum measurement in each case. So that's the sort of subject of ongoing research, is which instrument is providing the best sort of estimate of SO2 loading in these cases. So moving on now, I wanted to talk a little bit about more about the sort of passive degassing measurements. And just using this plot here from a paper by David Pyle and Tamsin and Juliet, sort of summarizing the use of remote sensing through an eruption cycle. So typically before an eruption, of course, volcanoes will produce passive degassing at low altitude and then move into eruptive degassing. measurements of our eruptive degassing are quite mature. We've got a lot of nice observations, particularly of SO2 and of the plume dispersal. But generally, the passive degassing measurements are less less well quantified from space. You can ask the question, when does sort of passive degassing, which a lot of volcanoes exhibit, become what we call pre-eruptive degassing? At what stage would you see a significant change, if you like, which you would call an eruption precursor? And to do that, you need some sort of baseline, or if you like, climatology of volcanic degassing to to establish the sort of typical range of emissions from a particular volcano. And we know that SO2 is a very good, very robust indicator of volcanic unrest or eruptions, particularly. This is some work by Maria Fertney at Cornell, and a contingency table just comparing incidences of SO2 detection for erupting and non-erupting volcanoes. So, SO2 gives you very few false positives. It's a very robust indicator of eruption, and a very, the absence of SO2 is also a robust indicator of a non-eruption, if you like. But generally speaking, though, the gas data is generally not used as much as other forms of data like seismicity and deformation as a volcanic unrest indicator or precursor. Perhaps, and one reason for that is that CO2 emissions are generally more useful than SO2, and we have very few satellite observations of CO2. And on that note, the volcanic gas community is one of the most robust indicators of volcanic or eruption precursor is the ratio of CO2 to SO2. There's a number of studies that show that this ratio increases prior to eruptions, particularly at basaltic open vent volcanoes like Villarrica in Chile and Etna. But these kind of ratios are extremely challenging to measure from space. I won't say impossible, but it's very difficult to have a satellite, or two different satellites, if you like, measuring CO2 and SO2, looking at the same air mass to get a ratio. And there's only one satellite that can currently measure sort of both CO2 and SO2 simultaneously. That's the Japanese GOSAT instrument. So it's very hard to measure a gas ratio from space. So that leaves us basically with trying to analyze the SO2 data alone. And so a lot of, we a couple of years ago published a new volcanic SO2 inventory based on the ozone monitoring instrument data from the AURA satellite, where we used long-term averages of SO2 data to quantify SO2 emissions from about between 90 and 100 volcanoes worldwide. And we calculated the total flux from those volcanoes, which is fairly sort of consistent over time, around 20 teragrams per year. And this is the vast majority of gas emissions from volcanoes are in this passive mode rather than eruptive mode, around 80 to 90%. And using these kind of techniques, we can measure down to quite low SO2 fluxes with OMI. And with the new tropomi data, we can probably extend it to lower than that because of the higher spatial resolution. So this data set is very valuable for just quantifying the general background levels of degassing at many passively degassing volcanoes. And a lot of these volcanoes show interesting trends. But the important thing to note is that we're only seeing, this is a sort of a 10-year record, 10 to 15-year record. So it's only a very small, snapshot of most volcanic life cycles. So volcanoes like Miyakojima in Japan, this is a very strong SO2 source in the sort of early part of the century, and on a long-term decline over the past decade. Other volcanoes are sort of on a sort of plateau with a fairly high emissions, like Dukono in Indonesia, and other volcanoes are sort of ramping up. over this past decade, like Sabancay in Peru. But like I said, these are only sort of snapshots of cycles at these volcanoes. And of course, all these are all open system volcanoes. Of course, by definition, they're all degassing. And another important sort of characteristic of all these volcanoes is that most of them erupted during the decade. So again, so SO2 emissions, of course, are a high, a strong indicator of eruptive activity. And but now for this, in this particular decade, we had no major eruptions of a magnitude greater than 4. So no eruptions of the magnitude of VEI5 or more erupted during this decade. So we don't have any constraints on the SO2 emissions during those larger eruptions. So I wanted to, so one sort of example, recent example where you can apply these, the idea of using the sort of long-term degassing rates as an indicator of, or sort of identifying anomalous degassing, is was the Uluwatu eruption in Papua New Guinea in June of again June 2019. So this is just a picture of the eruption plume, the Plinian eruption, umbrella cloud from that eruption, which is a fairly large eruption, VEI4. So now, just the day prior to that eruption from Uluwatu, on the left here, there's an image of from Tropomi of SO2 emissions, and there's some wind information on here as well. And we calculate a flux from that image. We can calculate an SO2 flux, which is on the order of 3 to 3,500 tons per day. And then using our long-term record of emissions from Uluwatu, we can say that this emission was around 5 standard deviations above the decadal mean. So we're certainly an anomalous level of degassing, and on that basis, you could say it was an eruption precursor. And these kind of techniques are sort of somewhat similar to the ones used by the seismic community, where they use you can use a short-term average over a long-term average ratio as kind of as a trigger algorithm, and in this case we can apply it to degassing. But previously the sort of long-term average aspect of SO2 emissions was not well known, but now we have this new satellite-based database that helps to quantify these long-term average emissions at these volcanoes. So taking that a little bit further, and what I've done here, and this is a bit of a busy plot, but taking all the time series we have from all the volcanoes which have detectable SO2 emissions from OMI, and I sort of align them all so that the eruption time, and these are all the ones that erupted during that time period, and the eruption time is at 0 on the x-axis here. And so basically trying to get some idea of the general change in SO2 emissions across an eruption cycle by, if you like, sort of collating all the little snapshots we have of eruption cycles at different volcanoes. And as I said, these eruptions are all VEI 3 to 4. We didn't have any larger events in this period to look at. So none of these sort of Mount St. Helens or El Chichon size eruptions. And I should add that some of these eruption magnitudes are somewhat uncertain as well. But the general trend, if you sort of take an average of all those trends, is the red curve here. And so this is kind of what you might say is the mean SO2 degassing trend across an eruption cycle for a VEI3 eruption. And it shows, well, the sort of general characteristics are sort of a relatively high SO2 flux on the order of a few hundred to 1,000 tons per day in the years prior to eruption, and sort of a relatively higher flux for a few years after eruption, perhaps due to, if there's some magma intrusion associated with that eruption, that's the degassing of the intrusion, and then a sort of slow decline afterwards. So this is kind of interesting, and it's interesting to think about the implications of this for volcanoes that are exhibiting these kind of levels of degassing now, several hundred to 1,000 tons per day, potentially sort of thinking about the risks of VEI3 eruptions from those volcanoes. And another thing to note is that you can only really do this analysis with satellite data, because it's very rare to capture an eruption cycle with ground-based gas measurements, because it's not often you're in the right place at the right time or have the right sort of data set to quantify these cycles with ground-based measurements. So if you look at, I've looked at other magnitude eruptions as well. So the three curves here are different eruption magnitudes: VEI2 in grey, VEI3 in red, and VEI4 in blue. And it's interesting that despite despite they're quite noisy, these data sets, but you do see some significant difference in the trends for the different eruption magnitudes, which is interesting. So that the VEI2 don't really show any significant post-eruption peak in degassing, whereas the VEI3 and the VEI4 do show that post-eruption peak. And there's also quite a bit of a difference in the sort of ramping up of SO2 emissions before the eruptions that does vary with magnitude. So there's kind of some interesting relationships there. And what I should also add that these are annual means I'm working with here, so not very high time resolution. And you can look at seasonal emissions, so sort of binning the emissions into 3 monthly periods to look on sort of shorter time scales. And the trends are basically kind of similar, but you can see that there is for these VEI4 and VEI3 eruptions, again, on average, there is a sort of period of ramping up within about six to 8 months before an eruption. We do see a sort of increase in SO2 emissions prior to the eruption itself, and then that post-eruptive peak. And as I said, it'd be interesting to see VEI5 or larger magnitude eruptions may be completely different. Generally speaking, I think VEI5 eruptions or larger magnitude eruptions, thinking of things like Mount St. Helens in 1980 and El Chichon in 1982, don't show much pre-eruptive degassing at all. They're more sort of closed systems prior to eruption. So these smaller magnitude eruptions are coming from more open system volcanoes. And so thinking of other approaches, of course, so that's all based on just degassing alone. But I think the multi-parameter perspective is very valuable. I was involved with a Powell Center, USGS Powell Center project, along with some COMET members, Juliet Biggs and others, Susie Edmeyer, to look at the relationships between SO2 emissions and the other two parameters we can measure from space, thermal or heat flux and deformation. And there's some interesting correlations between these parameters, and this is summarized in a paper by Kevin Reith a couple of years ago. And by putting together the different data sets, you can say something about the status or the open versus closed system status of these volcanoes, of course, much more accurately than you can with just a single data set. So that's a much more powerful approach, I think. And in the future, I think, I know people in COMET are working on this, the application of things like machine, deep learning, neural networks, or the broad umbrella of artificial intelligence approaches is going to be needed to process the large amounts of data coming from satellites. Degassing data is the same. The volumes of SO2 data are becoming very large now, and it's kind of impossible to analyze it, or for a human to analyze it efficiently. So it's I think these kind of approaches are going to be quite useful in the future. The final thing I wanted to touch on here was the idea of sort of something a bit different, was the thinking about quantifying health hazards of volcanic gases from space. So of course we're all familiar with hazard maps of volcanoes. On the left here is just a sort of a summary of the different types of hazard map from a nice summary by Eliza Calder of the different types of hazard map you get at volcanoes. But it's very unusual to see a volcanic gas hazard map. You know, I mentioned before, a lot of around 100 volcanoes or more around the world are emitting significant amounts of SO2, which is a health hazard, and yet there's no real sort of technique, if you like, for producing a volcanic gas hazard map. Now, there are some examples of this during eruptions. On the right here is the Holaroin eruption of Iceland in 2014, and during that eruption, there were forecasts of SO2 exposure from the degassing fissures on a sort of operational basis by the Icelandic Met Office. But to date, there hasn't been any really attempt to quantify this kind of hazard from a persistent passive degassing source. So I have a student working on this, and this is a bit of a plug really for some. She has a presentation at the virtual Goldschmidt meeting, if anyone is attending that, which is I think it's next week, June the 24th. But anyway, we have these nice, you know, average satellite SO2 maps now, which basically give you an idea of the average plume distribution around these degassing volcanoes, and also there's a lot of population data available now that you can use to quantify exposure to volcanic SO2. And on a sort of global basis, it's not very well constrained, and it is definitely a significant hazard to health, particularly because these volcanoes are degassing for decades or centuries even, and of course even in this in the current pandemic, there's an increasing emphasis on the importance of air quality and health hazards from air quality. So the idea here is to convert the satellite-derived SO2 columns into concentrations, because the satellite is measuring a total atmospheric column, but to assess health hazards, what you need to do is convert that into a ground level concentration, which is a very non-trivial problem. Depends on a lot of different factors like the pressure, the temperature of the gas, and the altitude distribution of the gas. So there's a lot of assumptions you have to make, but you can. It is possible to convert column amount to concentration, and then get an idea of the exposure of populations to SO2 around these volcanoes. And one place that this is very prevalent, of course, is Masaya volcano in Nicaragua. Very heavy volcanic SO2 pollution around this volcano, and again, members of the COMET group have been working here. And again, on the bottom left here, I've got just the average plume distribution from the OMI measurements. And here is on the right here is just some ground level concentrations measured on the ground. And obviously there's quite a good correspondence between the average plume measured from space and the ground level concentrations. And these kind of measurements are of course valuable for validating these kind of techniques. Just to start to wrap up here. So just thinking on a broader perspective. So if you look at this chart shows the total SO2 emissions from anthropogenic sources, that is power plants, smelters, and the oil and gas sector, and from volcanic emissions on the bottom in blue. And the interesting thing about these emissions, on these sort of multi-decadal timescale, is that at some point in the next decade, if current trends continue, the volcanic emissions will become the dominant source of SO2 in the atmosphere, as anthropogenic emissions continue to decline. So, however, just in the past year, we saw a significant decrease in global SO2 emissions from volcanoes, and that is mainly due to reductions at just two volcanoes, Kilauea in the US and Ambrim in Vanuatu, which were two of the strongest sources previously, and they just so happened to shut down. So the emissions, so global emissions are is sort of quite sensitive to the just these stronger sources. So the global volcanic SO2 emissions also declined a little bit. So there's a lot of open questions. Is what is the is this the sort of new normal for volcanic emissions? Are they going to recover to the previous levels? And but it does seem clear that sometime in the next decade, volcanic emissions will become again dominant in the atmosphere. So just to summarize there, so I've shown some, we've seen continued progress to quantify the spatial, temporal and compositional aspects of volcanic emissions from various sensors. I think the long-term satellite-based volcanic SO2 data sets are kind of useful for helping us to identify anomalous unrest, potentially forecast eruptions, and quantify degassing trends over eruption cycles. Again, there's some interesting applications of these data to quantify volcanic health hazards and perhaps produce volcanic gas hazard maps, which is a new, would be a sort of new product. And on a more sort of general scale, the volcanic emissions are strongly influenced by just a few major sources, and just last year we did see that big reduction. So it's interesting to see what's going to happen in the next few years. But one thing is fairly sure that the volcanic contribution to atmospheric SO2 is increasing over time. So continued measurements are very important. So thank you for listening, and sorry if I went over time, but
thank you. That was fantastic. And already we've generated lots of questions in the chat. So let's go through some of those. Actually, the thing that most seems to have caught people's imagination is your SO2 eruption cycle plots. So I think several questions about those. So starting with Tamsin, who asks, is the VEI2 eruption cycle trend also possibly a detection issue as you're only using satellite data? Yeah.
Yeah, I forget that there's the numbers of events in these different curves varies quite a bit. There's not many events, VEI4 events, that go into this trend. I think about 6. And there's most of the observations are the VEI3, so that's kind of the more robust one, if you like. There's about 30 or 40 eruptions, and yeah, the VEI2 I think is I forget the exact number, but it's less less robust, if you like. There's less data going into that trend. So there is a detection issue. The smaller eruptions are not or less frequently detected. Right.
Okay, and I'll come back to Tamsin's second question if we have time. So SO2, excuse me. So Brendan McCormick Kilbride asks, SO2 remaining elevated for 2 to 3 years after certain eruptions is very interesting. It could be magma recharge. Have you tried to determine if any of the volcanoes you've studied have geodetic or other data to support recharge? And there's a follow-up, and is there any variation in magnitude of deformation that could be linked to the degree to which chamber was evacuated by previous eruption?
Yeah, those are definitely interesting points, and I haven't looked at the deformation specifically for these eruptions, but that's definitely something worth exploring. Yeah, I'm sure there's a lot of deformation data available for these events, so that would definitely be worth looking at if there is some sort of correlation.
And I guess I had a follow-up question on the similar theme. Was it seems that the average they decay, the SO2 emissions decay to a lower rate after the eruption in the after 5 or 10 years than in the preceding 5 or 10 years. So what is that telling you about the status of the magnetic system following these eruptions?
Right. Yeah. 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 I mean that one interpretation is it's a degassing of a single intrusion, I guess, and then.
Okay. And so the next question, Pablo Gonzalez asks, says, very interesting talk. I'm intrigued by the VEI 2, 3, and 4 annual temporal SO2 behavior. Could it be the VEI 3 are more frequent in some volcanoes and that could bias pre and post eruptive trends? while the VEI4 pattern could be more robust?
Yeah, I would say the VI3 is maybe more robust. We do have more, there's much more data in the VI3 trend than the other one. You know, there's just, as magnitude increases, of course, the number of events decreases. So I would say the VI3 is more robust than the VI4 trend.
Looks like a sort of smoother curve, doesn't it, or more?
Yeah.
Yeah. Emily Mason asks, have you looked at separating the SO2 eruption cycle data by something other than VEI, e.g. magma composition?
Yeah, it's a great comment or suggestion. Yeah, I did think about, we haven't done that yet, but that would be worthwhile because, right, there's different volcanic, different magma compositions going into these trends. So it'd be good to break it down. Yeah, definitely good suggestion. Yeah.
Great. And there's this follow-up question from Tamsin. So one of the lessons from Holofun was that PM, e.g. sulfate, was key for health. Are you using chemical transport models to look at this in Indonesia too?
Yeah, we're not yet, but that would be, that's the next stage of doing that would be to use more advanced models to more accurately, well, you can use models to sort of simulate how much or predict how much SO2 is reaching the ground for different scenarios. So that the student I have working on was a master's student, so wasn't able to do a great deal of work. But hopefully, in the moving forward, we could use a more sort of complicated approach. I do have postdoc funding available if anyone out there is interested in kind of this kind of stuff. I've got some NASA projects funded, so
excellent.
So yeah, drop me a line if anyone wants to.
Yeah, and we can advertise those around the COMET mailing lists as well if it's if you'd like. So that's great. So unless there's any more questions popping up, we have been continuing discussions also in the Slack channel. I don't know whether you're a Slack user or hopefully you've been sent I wasn't the Slack user before this meeting, but you will have probably been sent the details and registered on that if you wish.
As of 10 minutes ago, I wasn't a Slack user either.
Okay, well, if you can navigate that, it should be fairly straightforward, and there may be more questions get posted there. But if not, I'm going to cancel your screen share if I can.